Engineers love automation, and Wealthfront automates your investing. As a software engineer, there are certain processes that you want to execute no matter what, like integration tests during a build. You wouldn't execute integration tests manually. You would use a continuous integration tool like CodeShip or Jenkins to automate your integration tests. Wealthfront is a tool to automate investing. Just like a continuous integration tool runs your tests automatically, Wealthfront can reinvest your dividends automatically and perform tax loss harvesting automatically. To get your first $15,000 managed by Wealthfront for free, go to wealthfront.com/sedaily and get started with Wealthfront's layer of automation on top of your portfolio. Wealthfront.com/sedaily. Check it out. It would support Software Engineering Daily, and you will get $15,000 managed for free if you sign up. Automate your investing. Get back to the things that you can't automate, like writing code. Distributed databases should be architected with the expectation of failure, says my guest Fangjin Yang. He is the creator of the Druid distributed database. Fangjin, welcome to Software Engineering Daily.
Hi, thanks for having me here.
You gave a talk at QCon San Francisco called Architecting Distributed Databases for Failure. What were your experiences that inspired you to give that talk?
So I've been working on Druid for a couple years now. Actually, the second committer on the project. It was started at a very small startup. And it was, if you haven't heard of Druid before, it's a distributed database. It's an open source one. And it was initially started to power like a user-facing application that needed to be up 24/7. And for a long time, I wanted to create a talk that was about my experiences working on Druid and the various failures that you have to deal with on sort of a ongoing basis. So that was the talk kind of came about with that. It was the lessons and experiences that I learned. And it was with the hopes that we're people building out new systems right now. Open source is getting really popular. Distributed systems also getting really popular. There's a lot of folks out there working on different projects. I was hoping to just give people some general advice because back in the day when I was working on this system, I learned a lot from just reading papers that people before me had published.
One of the first slides of your talk had the phrase, "Everything is going to fail." Why is it helpful for developers to acknowledge this up front, that everything is going to fail?
Right. I think it's just something you have to keep in mind as you work on a distributed system. I know the first time I started working on a distributed database, it was a very scary concept to realize like every line of code, every sort of module I wrote could potentially fail in some way or another. And if you just keep that in mind as you're writing code, then you have to start thinking about ways of preparing for failure. And the more you're kind of comfortable with this idea that everything is going to fail, the more you just realize it's sort of this natural process of distributed systems, and it helps you write and architect better code. I guess it forces you to always think about it in everything you do.
And along with this notion that everything is going to fail, increasing complexity, we have changing application requirements. Application requirements these days are much different than they were 5 years ago. We often see systems with tens of thousands of nodes and petabytes of data and 24/7, 365 a year, uptime expectations, and also expectations of high performance. So we want high performance, smooth uptime all the time. How does this level of scale change things from the good old days where we just had lower expectations?
Right. I think back in the good old days, you could really just have like one system do everything. That's sort of the beauty of not having that much data. You could have your relational database be your storage and also be your query point and like do everything you need with it. As data volumes have grown, it's kind of been interesting to watch systems start specializing in seemingly like very trivial problems. I think the interesting thing about this whole like big data wave that's happening right now is like every little problem associated with data at a certain scale of data becomes actually really difficult. Like transmitting an event from one place to another is actually like a really, really difficult challenge at scale. So I actually I forgot your original question. I'm sorry. Could you repeat that again?
Well, I was just asking how the level of scale changes things from the days of lower expectations. But I realize that's a broad question. So we can start moving into more specific aspects of your talk and Druid. So in this talk at QCon, like you said, you use Druid as a case study for a scalable database. Let's talk a little bit more about what Druid is before we get into the general lessons from the case study. What is Druid?
So Druid is an open source data store. There's a lot of open source data stores. What makes Druid a little bit unique is it has sort of a custom column format and a custom storage format. And it's particularly good at a few things. It's particularly good at powering like user-facing data applications. So it's very much designed that you can put some sort of visualization or something user-facing in front of it, and you can like interact with those visualizations. Druid is also pretty good at doing like streaming data ingestion. So if you have some events occur and you want to explore them right away, then Druid is pretty good for that as well. And it's a Apache 2 licensed open source project.
So Druid is designed for low latency Olap queries and data ingestion. Can you give some examples of these types of use cases?
Yeah. So Olap is, it's a more technical word. The sort of more buzzword associated with Olap queries is like business intelligence type queries. So these queries are they're often what you would use like a traditional data warehouse for. So if you're collecting like sales or revenue numbers, and if you want to know like how did product X sell in some particular state over some particular period of time, that would be an example of a business intelligence or OLAP queries. So with these types of queries, what's interesting about them is most of the time you're doing some sort of aggregations, and you're adding a bunch of stuff together, whether it's like sales numbers or counts of things happening. You're also kind of slicing and dicing and filtering onto your data. And this is like pretty contrasting to like transforming data or manipulating it in some way. You're condensing the data in a view that's like understandable by people, basically.
In your QCon talk, the first type of failure case, and you mostly focused on failures for a lot of the talk because that, as we said, everything is going to fail. So the first type of failure case that you discuss is this simple, common case of a single server failure. And, for people who may not be listening closely, as a distributed database, there are inherently multiple servers. So in the case of a single server failure, which can occur under conditions like a hardware malfunction or a kernel panic or a network outage, really a broad variety of things can lead to a single server failure. What do you have any statistics on how often single servers will fail in typical cloud environments like AWS, just to give people an idea of how common this case is?
I don't have any exact statistics. It becomes more and more common as your cluster gets larger and larger, and that's hopefully something that's pretty obvious. On a weekly basis, you might see it happening a few times a week. With AWS in the earlier years, it would happen a lot more frequently. As AWS has matured over the years, we actually do see it happening less and less now. But it is really a factor of the scale at which you're deploying the software. Like the more servers you introduce into a cluster, the more chances there are going to be of failure.
And the standard solution to this single server failure is to replicate your data.
Yes.
How does Druid perform replication?
Right. So the more traditional way is replicating your data. Some of the systems kind of coming out of academia right now is actually focusing on like very, very fast recovery. But for the most part, systems that people run in production, out in industry, they tend to focus on replication. The way that Druid does replication is it partitions data into like immutable chunks or shards. And the way that Druid replicates is it looks at one of these immutable shards of data. And if you're not familiar with what a shard is, it's basically like a slice of your data. It's this never changing slice of your data. And because it's never changing, you can just create the exact copy of it. And whether you access one copy or the other copy actually makes no difference. So it's a really easy way of just creating multiple copies of slices of your data.
So as you mentioned, the segments of data are distributed and replicated among shards, and you call these shards historicals. And if a client wants to access the data that's distributed among different historicals, the client queries a Druid broker, and the brokers access the historicals. Can you describe this interaction between the client and the brokers and the historicals in more detail?
Yeah. So just a minor clarification. So these shards of data, or these like partition slices of data in Druid, they're called segments. And the way it works in Druid is segments get loaded across a set of servers called historical servers. The purpose of historical servers is pretty simple. They download like a view of data or a slice of data, and then they run queries over that data. And these queries are kind of determined on what the client issues. The way that the client interacts with the entire cluster is through this type of server called like a broker server. The purpose of the broker is to understand where these like segments live on different historicals. So if you have, like, for example, about a week's worth of data, the way you might partition this data is into 7 slices or partitions. And each one of these partitions might live on a different like historical server. So what the broker does is it figures out, okay, well, if a user issued a query for like 3 days worth of data, maybe that's only 3 partitions. And where do these 3 partitions live? So it does this query scatter and gather functionality where it forwards the query down to the historicals, which contain the data related to the query. And the historicals do their portion of computation and return results to the broker, which does a level of query merging. So it's sort of a scatter, gather, divide, and conquer algorithm for processing queries.
So now that we've described the replication process and the querying process, can you describe a simple failure scenario where this replication allows for recovery or fault tolerance?
Yeah. So the most common failure is the single server failure. So for example, I'm a client, I'm talking to a broker, and the broker forwards my query now to a historical, but that historical server has failed. It's no longer there. So if your data wasn't replicated, then you're not getting results back as a client. The nice thing about replication and with this model that Druid has is, a slice of data or a partition of data is replicated across multiple historicals. And as soon as one server disappears, the broker sees that and says, okay, a copy of data, some window of data is now gone, but other copies exist in the cluster. So as I start seeing queries for that data from clients, then I'm going to start rerouting queries basically to where that data actually exists on other historicals.
So a slightly worse failure scenario than the single server failure is the multi-server failure. And this can often occur with a failure in a data center. What are some strategies to get fault tolerance against this multi-server category of failure?
Yeah, so multi-server failures are a lot less common. And you might see them. I typically see multi-server failures maybe once a year, maybe sometimes less than that. But when you're trying to do 24/7 uptime, then multi-server failures are incredibly impacting. They're incredibly impacting because it's very hard to guarantee data availability with multi-server failures. In that even if you replicate data many, many times over, if you lose half of your servers, then you're going to be losing data. So there's sort of 2 ways that you can approach this problem. There's the, more expensive but ultimately better way, and there's also like sort of the cheaper way of doing things. The more expensive, ultimately better way is to completely replicate your data across multiple data centers and in different geographic regions as well. So even if an earthquake hits like the west coast of the United States, your data is replicated in the east coast, then it should be fine. But that requires, if you have a very large cluster, basically duplicating your cluster into like another availability zone or in Amazon's availability zone. But if you have your own data center, another data center somewhere. This can be very expensive, and not companies of a certain size don't always want to do it. So one thing that companies sometimes do is to try and recover really quickly. So if you don't need your data up 24/7, if you can have a few minutes of downtime here and there, then there are things that you can do to try and set up for very, very fast data recovery. And Druid is a system that has, it's able to be replicated across multiple data centers, but at the same time, it also does like fast recovery mechanisms.
So we'll get into the multi data center strategy, but we should go into the fast recovery strategy in a little more depth. So you said the method of fast recovery can be a viable strategy in the face of this multi-server failure. So what do you mean by fast recovery? How do you implement fast recovery?
Right. So what I mean by fast recovery is basically things are broken, and you have data loss or something else, but it's not the end of the world, because there are ways that you could potentially recover your system in a very short span of time. In a system like Druid, that span of time might be minutes. And I know in academia, there are systems where they try and recover their state and try to go back to a really good state within milliseconds. In industry right now, fast recovery is probably minutes. And the overall idea behind fast recovery is things are bad, they're going to be broken for a little while. Let's try and get things back to a good state. The way it's done in Druid is Druid kind of backs up all its data in another system. And the way it's designed to work is that if you're able to bring up new hardware, if you're able to bring up new resources, then Druid will start prioritizing recovering any missing data right away. So let's say if you lost half of your cluster and you bring up, a new set of servers to replace those lost servers that you lost. The idea in Druid is Druid will start prioritizing any missing gaps of data before it starts doing any sort of like replication or load balancing or any of that. So Druid prioritizes recovery over like a good steady state.
Right. And so you talk about this fast recovery involving placing a layer of deep storage, such as S3, between the point of data ingestion and the sharded historicals. And so with this fast recovery strategy, with the S3 or the HDFS backup layer, whatever you're using for this deep storage layer, you mentioned a dangerous scenario that can occur. And what can happen is that your database nodes can all fail, and you're left with this deep storage layer, and then you go into recovery mode. Mm-hmm. And then while you're recovering, you spin up a single database node, which is suddenly the only thing available for all your incoming queries. So what is the consequence of that scenario, and how can you architect around it?
Right. For what it's worth, I don't really like fast recovery. I know some people out there use it, but I always believe that you should replicate your data across multiple data centers if it's really critical. One of the dangers of fast recovery is it's very easy to create hotspots if you're not careful. So if you had 10 servers initially and you lost those 10 servers, and maybe you're bringing up only 5 servers now, if you're not careful about how load is distributed across those 5 servers, you can get into situations where your most crucial data starts ending up on 1 or 2 of those servers. And you're now creating basically like hotspots in your cluster, and performance starts to suffer a lot. So if you're building a system which is doing fast recovery, then it's really important to consider, as your system is recovering, how is load being distributed, how are resources in your cluster being used? Because another danger is, let's say if you lost a handful of servers and you bring up new ones, you don't want to start using all the resources of your cluster trying to recover that cluster. Unless it's like, the end of the world scenario sort of recovery. Basically, what you want to do is spend a small portion of resources of your cluster recovering things and loading data back up, but still devote the majority of your resources to answering queries for data that is there. Otherwise, your users of your system are just going to be really, really mad that all of their data is not accessible versus a very small amount of data is not accessible.
Engineers are always looking to simplify To simplify testing and deployment, engineers turn to CodeShip. CodeShip is continuous integration and delivery as a service. With CodeShip, your tests are executed against your code automatically whenever you push to GitHub or Bitbucket. On Software Engineering Daily, we've done several shows about DevOps, and continuous deployment is key to DevOps. It's a great way to break down the wall of confusion between development and operations. Managing your own testing infrastructure is painful. That's why you want a service like CodeShip to do it for you. If you have a huge number of tests, you can use CodeShip's Parallel CI to run all your tests in parallel. CodeShip will spin up containers on their own infrastructure to run your tests in parallel. If the code passes your tests, CodeShip will deploy it automatically to your users. Companies like Product Hunt are already using CodeShip to speed up and simplify development. To sign up for free and start shipping today, go to codeship.com. Or to try out CodeShip's new Docker platform, go to codeship.com/Docker. So, as we've discussed in a couple places, the importance of replicating across multiple data centers, that seems like a personal preference of yours. And so, to motivate that discussion, I think we should just discuss the data center outage, which is possible. A hurricane comes across and wipes away one of your data centers. You don't want that to wipe away your entire business. So it is important to be prepared for that. And as you said, maybe you want it just as an alternative to even multi-server failure. A rack fails or something in a single data center.
Right.
So this multi-data center replication, if I want to replicate across different AWS availability zones, I think that's the most common case of how we would be doing this replication. What are the problems and the risks that I would encounter?
Right. So with a lot of distributed systems, how they work is there's almost always some sort of central coordination piece. And that coordination piece, if, for example, Zookeeper is very, very popular as a coordination piece, but there's other alternatives. The way that coordination piece often works is it does like heartbeats to different servers out there to know like, hey, what's out there? What does my cluster look like? If you just sort of naively replicate your servers across multiple data centers, the network time can be something that becomes non-trivial and starts impacting how the coordination piece works. In a setup like AWS, if you replicate your servers kind of naively across US East 1A or like US East 1B, the way Amazon kind of sets up its availability zones is, these two availability zones might actually physically just be across the street from each other with like fiber wires connecting them. So yeah, like the network latency is like very, very minimum. But if you do like US East 1A and US West 1A, then there's a possibility that there's going to be non-trivial network time in communication between your various pieces in your cluster. And if that's the case, then you don't want your cluster to start doing bad things because its heartbeats aren't getting responded, or its coordination piece gets really, really confused about what the state of the cluster actually looks like. Yeah.
And so just to motivate this idea, like heartbeats, I mean, these are like extremely regular processes. Like if you have a distributed coordination system like Paxos or Raft, these can lead to like really, really frequent heart beating. So is this, with these types of problems, what are some approaches that you recommend, some best practices for multi-data center replication? Yeah.
So I don't recommend distributing the coordination piece across multiple data centers or even sort of running one cluster in multiple data centers. What I see work a lot better is from one data center to another, you basically have an exact copy of like everything, and the two clusters might never know about each other at all. So what I mean by this is you do a complete replication. Like you have your complete coordination piece set up in both data centers. You have all the exact same servers set up in both data centers. And what you use to to try and actually coordinate these two separate clusters is your ingestion piece or your actual like application. But the underlying like data store or the underlying like infrastructure doesn't have to know about each other or even know that it's like being replicated across multiple data centers.
So what does that look like in practice? How does the ingestion side of things know that, oops, I wrote to these two data centers an inconsistency?
So this can be very challenging depending on how you do ingestion, or it could be simple based on sort of the model that you use for ingestion. Like one sort of more simple way is if you're doing like batch ingestion. And what I mean by batch ingestion is you have some static data set that you're basically loading. There you kind of load one copy in one data center, check it's there, load one copy in another data center, kind of check it there sort of thing. There's not as many sort of hidden gotchas that can occur. Outside of, because like latency is a lot less important. What's a little bit more tricky is if you start doing like streaming data ingestion, basically. So how do you know that the 3 events I sent to data center 1 are the same as the 3 events sent to data center 2? Most of the open source projects out there are still working on making some of these things better. There's been tricks that have been used by different companies, as in like Kafka, and like what people have done at LinkedIn is, from what I hear, basically in every single data center, there's like a Kafka cluster or a Kafka producer that's set up, and there's sort of like one central Kafka cluster that gets used for like core analytics. And if there's any discrepancy in the data, or there's any sort of faults in the data, then there's batch processes that can occur to like clean up some of these problems. Right.
Okay. Well, so we've mostly been talking about failures. I mean, that's the consistency issue we just discussed might not be categorized as a failure, maybe just inconsistency. But in any case, the most brutal type of problem is probably more in that ballpark. It's actually not a failure. It's a slowdown or some other type of incomplete failure, an inconsistency in customer data or something like things. These are things you really, really don't want. So what kinds of things can lead to this type of inconsistency or poor performance? I know that's a really broad question, but what are the trends in things that you saw while you were working on Druid?
Right. Yeah. With distributed systems, I think, knowledge about how to build like stable distributed systems has been around for a while. And if you look at some of the more widely used open source distributed systems, they're pretty stable and they work pretty well in production. As in, they're not going to outright just fail and like lose your data. With a system like Druid or with any distributed database, the hardest problems to debug are not the obvious failures, but when something is like, something feels wrong, but there's no exceptions, there's no actual like hardware failures, there's nothing immediately obvious as what's going on. One example of this is like you're powering some application and users comes to you and say, hey, like my queries are really slow, my application feels really sluggy. And there's a lot of different explanations for why that can occur. It could be, a server is being a little bit flaky and that it hasn't failed any of its normal health checks, but it's just responding slowly because there's things that are starting to fail on that server. But it doesn't even have to be like anything like that. It could be there's just a lot of people using your cluster at the exact same time, and if there's a lot of users using it, then there's not enough resources for all those users. And this is a problem that's, this is a situation known as multi-tenancy, where you have many people potentially using the same set of resources at the same time. And it's a very difficult problem. It's one that I think a lot of open source projects have not solved like super well yet. Multi-tenancy creeps its head based on like usage patterns. So maybe at the end of a quarter, all your users are doing their quarterly reports and they're all doing it at around the same time, which can tremendously impact your cluster. Like your performance just degrade purely, not because anything's wrong, purely just because it doesn't have enough resources to handle, all your users at the exact same time.
I imagine it's really hard to load test that or to reproduce it also.
Yeah, it's extremely difficult to sort of predict what the maximum usage is going to be. And if you look at most modern internet systems, none of them are really designed for what happens if everyone in the world uses this system at the exact same time, right? You kind of plan for roughly the usage patterns that you see on a day-to-day basis. But like end of quarters and end of years are always where like things just, it's a very irregular usage pattern.
Yeah.
And it's hard. You try to do your best. Druid has certain, properties built in that try to like mitigate, when this sort of stuff happens.
Like, does anything come to mind that would be interesting or worth mentioning?
Yeah, I mean, so multi-tenancy is something we're constantly working on. It's something we thought about from the very, very beginning with Druid. One of the ways it handles multi-tenancy is in the way that queries are kind of processed. A query in Druid is always decomposed into a set of segments that need to be scanned. And these segments are just, shards of data. And each segment in Druid is designed such that it can be scanned in a few hundred milliseconds at most. The reason why we do this is if you have a very expensive query, and that query can be broken down into a lot of very small units of computation, then what happens is you can do a portion of that query and immediately release resources to do a portion of another query. If you have many, many queries occurring at the same time, all those queries are getting pushed along all at the same time because you're scanning a portion of one query, releasing resources, scanning a portion of another query, releasing resources, and so on. So even when you have a lot of users using your cluster at the same time, you're preventing the one crazy user from starving out your entire cluster. And what happens instead is everyone feels the slowness at about the same rate.
So as you've described here, that this is this strategy for ensuring that queries that are issued around the same time make consistent progress over time.
Right.
And I think this is characteristic of, the idea in distributed systems that there's often a trade-off between safety and liveness.
Right.
And I think it sounds like in this case you chose to opt for liveness over safety. Would you say that's accurate?
Yeah, I was thinking, so safety can mean a lot of different things. How we kind of think about it in Druid is that nothing should outright fail. If you're a user trying to query for your data, then you should be getting a response. If that response is a lot slower than usual, then it's a lot slower than usual. But you shouldn't have the scenario where you issue a query and you don't get any results back, right? Because that you're just the system is broken and I don't want to use it. So that's what we kind of plan for in Druid. But
right.
Yeah, multi-tenancy is difficult. Every system kind of out there, all the open source ones I know of are continuously working on solving it.
Yeah. So another source of poor performance that you touched on earlier is this idea of hotspots. What is a hotspot?
A hotspot. So in a distributed system, one common thing that can occur is a set of your servers are underperforming compared to the rest of your servers, and that's the sort of underperformance is starting to impact queries for everybody. So one example is, as part of your query as a client, you need to hit data that exists on 5 or 6 different servers. But if one of those servers is a lot slower than the others, then basically everyone is bottlenecked on waiting for that one server to respond. And so that's the idea of a hotspot, where a server is much slower than the others for some reason. And there's a couple of common reasons. One reason might be that one server just is responding to a lot more queries than all your other servers because it contains data that's a lot more valuable and just people are trying to hit that data. For example, that server might contain the most recent hour of data and every other server contains older data than that.
So not only that, but you can also get a hotspot problem in data center variability.
Yes.
How often does that occur, and what are some solutions to dealing with this data center variability?
So I think data center variability is a lot less common than like a single server like variability. The reasons why data center sort of variability might be occur is if I'm not on the West Coast and periodically I'm hitting servers on the West Coast responding to my queries, and those are super fast. But now my West Coast servers have gone down, and I'm on the East Coast, and my queries are much slower. The way that we kind of solve this problem in Druid is there's like preferences that you can specify. There's configurations that you can specify on a like almost a per server basis, but also on a per data center basis as well. That you can specify like rules saying like, hey, if things are normally functioning, then hit like this set of servers. If things are not normally functioning, then hit like this set of servers. So it's one of the ways that you can try and mitigate data center variability. So if you see that your user's IP is like a West Coast based IP, you try and route their queries to the West Coast data center. If they're an East Coast IP, you route to the East Coast data center, and if things are down, then you kind of route to the other one.
This brings us. Oh, sorry. Go ahead.
No, I was finished.
So this brings us to the term hedged request. Can you define the term hedged request?
Yeah, so hedge request, I think the first time I read about it was in a Google paper published by a very, very well-known engineer at Google called Jeff Dean. And he wrote this like really awesome paper about how to deal with variability within a cluster. And one of the main principles he talked about was to use this idea called hedge requests, which is you replicate your data, like you use the underlying replication, and you send queries to every single replica of that data. And what you're doing is you're waiting for the fastest response. So if one of those replicas responds, you basically cancel queries to all the other copies. And this is with the idea of tackling like really long tail queries, like those really, really slow queries. It introduces more churn in your cluster because you need to have more resources dealing with more queries. But the trade-off is you mitigate variability of those queries.
What I think is so interesting about the hedged request idea is it's almost like, oh my gosh, if we have infinite compute, we can scale up the request reliability to meet that available compute. I mean, hypothetically.
Yeah.
Like we did a show with Matt Ranney from Uber, and he actually mentioned the hedged request pattern as well. And it's interesting to hear it in two places. Is this becoming a common pattern? Like are people starting to use hedged requests on a regular basis?
I'm actually not sure of all the distributed like data stores that use hedge requests. I think it's something that people are starting to realize now. Is as like the sort of lifetime of a system is you kind of make it work and then you make it fast, and now as the system matures, you're looking a lot more at this like slowest 1% of queries and what you can do about the slowest 1% of queries. And your sources of inspiration tend to be from academia or from sort of extremely famous distributed systems people. So I think, Jeff Dean, when he published that paper, that paper was pretty widespread, and I think everyone kind of got the idea there that we can do these things. And the more mature systems have started incorporating the ideas into their infrastructure, into their architecture.
So let's zoom out. What are some other strategies for minimizing variability among nodes?
There's other strategies that you can use, like selective replication is one that's pretty popular. And the idea there is, hey, if you have some pieces of data that are getting queried like really, really often, then try and smartly create more copies of that data, right? Like maybe your most recent data is what people really care about. And instead of having just 2 copies of it, you create like 20 copies of it. So what you're doing is you're smartly allocating more cluster resources to deal with your more valuable data. And as a result, then your general queries get better, and your those critical pieces of data don't have to live only on a handful of nodes that end up creating hotspots. And then one other thing that's pretty nice that some distributed systems do is basically you look carefully at, like, the system understands, is kind of a little bit aware of what's happening within itself. So it knows, like, hey, I've been seeing queries to a certain set of servers that are much slower than other sets. And this could be because the hardware is bad or because those servers are overloaded. So what I'm going to do is I'm just going to blacklist them. Like, no more queries are going to go to them for like 10 minutes and just see if things improve.
Right. So in these talks, you mentioned, in this talk, you mentioned that there's this selective replication, and then there's also what you called latency-induced probation. I think that was the second thing you mentioned.
Right.
And as you said, your cluster needs to be collecting data on itself throughout time in order to implement these things. How do you implement this cluster reflection? What are some practices around making sure your cluster knows information and analytics about itself?
Right. So we haven't implemented it yet in Druid. It's something we've talked about for a long time. And there's sort of two ways you can go about doing this. One way is to basically have the metrics of your cluster in something external that your cluster then like references. And one of the nice things about doing it this way is if there's some weird bug or your cluster's in a bad state, you don't want to have a cluster in a bad state making decisions about itself while it's in that bad state. So that's one of the advantages of potentially having like an external thing that the main cluster can use to make decisions. The sort of other method is for everything to be self-contained. So for a cluster to purely collect metrics on itself or to collect statistics on itself for a short period of time. And there, you only have a small window of time that you can use to start making decisions. So those are sort of the two ways that we've been thinking about thus far.
So we've been talking about two topics here. We've been talking about handling failures, all the different failures and what you can do to assuage them. And we've also been talking about the Druid distributed database, which is a case study for ameliorating these failures. And I'd like to bring these two things closer together. What are some macro lessons that you learned about distributed systems and failure handling while you were building Druid?
Yeah. So I think the main lesson I learned, I think when we started building out Druid, what we were thinking was more, it'd be nice for this thing to be really adopted, for everyone to use it. But I think at the end of the day, we realized it was more important that this thing work. And sometimes, there's very popular open source projects out there which are very simple to use, very easy to set up, but they don't necessarily have very good properties when it comes to dealing with failure and working at scale. So one of the main lessons I actually learned while working on Druid was complexity is sometimes there for a reason. Sometimes a system must have a lot of inherent complexity to solve a seemingly very, very simple problem. And that's sort of just the natural evolution that comes with more mature distributed systems.
I did an interview with Neha Narkade, who is she's the CTO of Kafka, Confluent, which makes Kafka, Kafka products, Kafka as a service.
I know Neha.
Yes, of course. So one of the things that she said that was interesting in our conversation was, I think it was, operations is the hardest part of distributed systems. It's not like writing the code. It's not like deploying it. It's actually the operations side of things. Is that consistent with your experience?
Yeah, absolutely. Writing the code, honestly, there's enough good practices, enough information out there that you have a basic idea of how to architect this thing. But once you architect it and run it, the sort of day-to-day, those really, really hard problems are not around things failing. You can build systems that more or less don't fail, but they're always around when things are slow or, things are kind of not working as they should be. And the only real way to debug a lot of those problems is to have really good operational practices in place, like really good metrics collecting, really good alerting, sort of deep understanding of the system to be able to preempt a lot of the failures that can occur. So I absolutely agree with Neha that building the thing is not hard. Running and maintaining it at scale becomes a lot more challenging.
What are some things that operations teams that run in production with a distributed database can do to ensure that operations is a little bit easier?
Yeah, so one thing I see a lot of organizations out there do is they collect like metrics, and those metrics represent general trends of what's happening in the cluster. Like, here is my average query latency, here is the amount of data I ingested, so on and so forth. What I see a lot less frequently of operations teams is having solutions to be able to diagnose a problem once that problem is seen. For example, let's say I have a giant spike in query latency, right? Like, why does that spike occur? Being able to answer like what's happening to cause my data to spike, I think is equally important as having really good practices in place for preventing those scenarios from happening. And I think monitoring, a lot of what monitoring does is helping to prevent certain scenarios from happening. And there's another class of analytics that I call exploratory analytics, or I don't call it, it's kind of known as exploratory analytics, where you're able to start drilling in and exploring data and understanding why something might be happening when everything starts breaking down. And I think both of those are really important for operations.
That's great. So to begin to close off, do you have any final comments about distributed databases to share with the listeners?
So I think distributed databases, if you're interested in learning more about them, or if you're interested in learning about distributed systems as a whole, open source is a really, really good way to start. With a lot of open source communities, they're pretty open to discussing their architecture or, helping out solve problems. So I think if anyone's out there in learning more, there's a lot of information online. There's a lot of online communities that they should look into interacting with.
And I'd also love to hear a little bit about Druid and where it's going and how you're seeing people use it and what your company is doing.
Yeah. So with Druid, what most organizations do with Druid is they provide they put some sort of data application in front of it. And what Druid really adds is the ability to do very fast like aggregations and these type of BI queries where you're slicing and dicing and drilling and filtering into data. What we do at Imply, like Confluent, like Elastic, and like Hortonworks, and many of these other organizations out there, is that we open source a lot of things around Druid. We're continuing to build Druid, but we help out with the operations side of things. So we help out with the really hard problems that no one really likes dealing with, like trying to understand why things are slow or why things might be wrong within a cluster.
Cool. Well, it's been awesome talking to you about distributed systems. Fangjin Yang, thanks for coming on to Software Engineering Daily.
Yeah, thanks for having me. It was great chatting with you.